So we are back. Hello, everyone, again. We are back for the next part of our conference today. The next section is called Innovative Technologies and Processes of Metallurgy. I will be your host for the next, I don't know how many minutes or hours it will take. Before we start, I would like to. So we are back. Hello, everyone, again. We are back for the next part of our conference today. The next section is called Innovative Technologies and Processes. I would like to offer to start this section to our beloved friend, to leader of young scientists in the International Institute of Welding, to Mr. Ernest Levert, who is in the middle of the night over there in Dallas. Thank you for not sleeping. Hope you are feeling well. You don't need Red Bull. And please go on.
Yeah, thank you. I need to share my screen here. So let's share the screen. Let's share screen 2. And I need to share my audio, share sound. Optimize. Okay, and we will share. Let's see here. And let's get ready. Are we? All right, are we good? Well, good morning to everyone. And once again, a greeting and welcome to the 2021 Young Professional Conference. It is 3 o'clock, 3:30 here in USA, and I'm just glad to be part of the team here. So we're going to talk about the Orion Space Program from a productive standpoint. I work for Lockheed Martin Missiles and Fire Control here in Dallas, Texas for 35 years. And if you are part of the YPIC conference in Budapest in 2019, I talked about the International Space Station. And so today, we're going to talk about the Orion project. This is a project that do electron beam welding. This is a dear project to me. I really enjoy the space program. As chairman of the IW Commission for Power Beam Technology, I chaired the Electron Beam Welding Conference, and I served as president of AWS in 2002. So I've had a chance to travel to 37 countries in my 50 years in the industry, but the most fun parts I've had have been the space program. So today we're going to have this actually a true success story. And so many of you know welding engineering. This is a true engineering success story. So we're going to talk about two things: the Orion launcher board system, which sits on the top of the Orion capsule. We'll talk about the Orion modular also. So those are two things we're going to talk about quickly this morning. So as you know, the Orion project is part of the human transport to the International Space Station. And once again, we hope to use the ARIS-1, which the launcher board system carries the astronauts to the outer space, and meet with the ARIS-5, which is the workhorse that carries engines, and they hope to go to Mars and beyond. So that's the future that we're working on with NASA, and we at Lockheed Martin with subcontractor working on several components of the Orion project. So how this all started for me personally is I'm a Lockheed Martin fellow at Lockheed Martin, and so I'm the number one go-to consultant for welding engineer material joining for the corporation. So I got a call from NASA and Lockheed Martin Denver saying we have a problem. To Judge Space thing, we need your help and your electrical expertise. And I was very excited to get the call. For one, when we get to NASA, said, Ernest, we have a problem. We need you to help solve this problem. So I got a call, and so it had to do with the launcher board system. So many of you may not know what is the launcher board system. It is the emergency escape during the launch, okay? So if I set the stage for you, you're sitting on the top of the capsule and you launch and you have an issue, then the launcher board system kicks into place. So let's see if this video will play for us. Are top of the launch. If you have a problem, you say, okay, all systems are go, but for some reason we have an issue. Now the launch abort support system kicks in. And these four nozzles are what we're going to talk about today, these major four nozzles, but the one of the exhausts is the fuel, you have the module that's at higher orbit. It ejects the capsule back to the Earth, and now once again, they're safe. However, they're over land right now. So how do you land the launch abort system over land? So the part that I work on has already been used and ejected, but now you look at the astronauts coming back down to the Earth. This is what you want them to understand and see. So we watch this for a minute. The thing about you as engineers and material science, it can be the heat shield, it could be the launch abort system. We have so many scientists around the world working on the International Space Station and of course the Orion project. And once again, how you're going to land on land is you have to have a landing system. And once again, there's your landing system. And as we get ready to have a successful land back on Earth, everyone is successful and safe. So with that being said, you have the launch abort system itself. You have, which is what we're going to talk about this afternoon, is the launch abort system. And then we have the crew modular, the service modular. And then once again, once this is used, you hope you never use it, but we're going to talk a bit more about how we make it happen. Here's a specification, just talks about the dimensions of it. The takeaway from this slide is, once again, the crew core is here. The launch abort system is here, but we're going to talk now about the nozzles. These nozzles is major concern. This is what provide the thrust from the rocket motor that take place. Once again, these are in dimensions, they are in inches. Sorry about that from my international colleagues, but this is about 555 inches on the length of it. And it's about 3 feet in diameter. So this is a big, this is a very, very, very large system here. So let's peel back the onion here and look at the launch tube itself, the motor. So you have a solid rocket motor here, but then you got these four nozzles right here. So this we want to talk about this morning is these nozzles. These nozzles are made of a certain material. So let's once again, we're engineers, so we're talking about the material components of this nozzle right here, the launch abort nozzle. So once again, this is a unique material. It's 4340 aluminum, steel, and there's electron beam weld. This was welded on afterwards, but there is a weld joint here and one sitting right here. So this is a EB weld and one right here. And the next slide will show a bit more detail. So you look at the four nozzles and you look at the breakaway here. There's electron beam weld here. They weld the 45 together. Then another EB weld that is sitting right here, this nozzle. And the key takeaway from here is the spacing between here. This clip is not long at the time, but you're trying to do an EB weld in this joint right here. And this is 2 inches thick. 2 inches thick, several millimeters thick here, but it's 4340 material. And so why was this an issue? The problem we have with this material is the fact is, one, you had a EB joint that's 2 inches thick. And more importantly, it's 2 inches thick, 4340 steel. And once again, it was elliptical. So you had major issues with the thickness varying throughout the thickness range. But EB was selected because of the restricted area. But the problem that we had was it ranged from a 1/2 inch to 1 inch range to 1.7 inches to 2 inches on the OD. And another problem you had a very small clearance of a 1/4 of an inch to go. Let me show you back here again. Trying to get this beam through this 1/4 inch material right here. And the problem you had, everyone, was magnetism. This is 4340. It was very high in magnetism. And so you had a major issue with magnetism. And with 4340, we have a preheat of 600 degrees, in-pass temperature, and post heat heat treating. So therefore, that was a major concern we had dealing with this material. So when they called me in, they would have an issue with porosity, beam deflection, and they didn't know how to make this happen. So they end up coming up with a solution. And like I said, if you guys were with me in Budapest, I talked about the heat rejection system, but now we're going to focus on electron beam welding of this process. So, electron beam welding is a very small beam of electrons inside a vacuum chamber, welded 60 miles an hour space. But the process is very key to what we're using right now. I enjoy electron beam welding because once again, because of the small heat effector zone, the most important thing is these electrons can be deflected with magnetism. So with that being said, we had some major problems with the steel. You see the elliptical on the 45-degree angle. We had one weld here inside here, then this other weld had to come in. And so we start welding this component. You can see here in this picture here, the clearance is a 1/4 inch and trying to get this weld joint in here. And once again, you see the magnetism is very high in the part. So we end up taking some material called MU material, putting it in here, and had the beam go in between that material to make that weld joint. So that was really critical, and it was causing a lot of problems. The fact that, I had to do the preheat of the part there, magnetism, the elliptical were major issues. So as a weld engineer, I'm deciding how we want to make this happen, how we're going to fix the problem. So here I am standing inside the EV chamber. This is the nodule before they put the manifolds on. And using the steel, once again, we had this called mu material, and we were using this to make sure we can have any beam deflection. So you think about yourself in a production environment, how you can produce this component with all of this contraption here with the preheat, inside the vacuum chamber. You got to maintain that the magnetism was causing problems. And you look at the idea of the weld joint, you had the penetration, but this is not what you want doing with electron beam welding, okay? So you had issues there. You had a lot of pores, a lot of outgassing. And so this is not what I feel was the ideal situation for this process. We had all these cables here on the floor. We use this to degauss the steel to get the magnetism out of the part. And so when I got called in, I saw all of this information, and I gathered up, and the NASA director asked, okay, Mr. Levert, you've been here for 1 hour. What should we do? Well, I share with him, based on everything that I see here, this is probably a material I would not have selected because, once again, it's 4340. This is the manifold after being welded. The weight is very, very high when you deal with something on top of the capsule. You can see here, this is Michael, the director of Monthiacol, and you see the nozzles here are welded together and welded in place. And once again, this is a pretty big nozzle. But think about this: you're sitting on top of the capsule itself. They asked, what would you recommend? And so I went back and did my analysis, looked at the yield that we needed, the KSI properties in the weld joint, on the back side of where the thrust is, on the lows on the EB weld. So I looked at that and decided, like, gentlemen, based on all of my analysis, I think we should change and go to titanium. And they said, why? And when I share with them all the reasons for using titanium, one, the weight reduction that it would take, going from 4340 to titanium will be very critical. But yet it was a 10-to-1 ratio, saving the weight, because it costs $500 to put 1 pound into our space. So once again, the cost savings, and once again, it's going to reduce the payload on top of the capsule, and the G-force is going up. Second is, you don't have to worry about any magnetism. So once you clean the parts and clean the parts, machine the part ready for EB welding, you wouldn't have any issues with the magnetism anymore. and the loads were a lot better, mechanical properties were better than the 4340. So it took a year to change that. So once again, we had a meeting together with, we found a company out of Indianapolis, NASA, Johnson, NASA, Lewis Research in Huntsville. So the team, ATK, has more entire cost. So we all got together in a room, and I recommended we go to titanium. So we were able to get titanium billets. We machined the billets, we cleaned the billets, and found the company in Indianapolis, and we tacked the parts together and put them on the fixture, did the weld inside the EB chamber, and look how smooth the idea of the weld is inside the wall here. So it's just very, very smooth. It just came out beautiful. And so once again, they asked the question about were we successful? I said, yes, we were very successful because one, we had a great part. It was once again titanium manifold. The guys did a great job welding it up with the tooling and the fixturing, and it just worked out tremendously. So once again, we were successful welding the titanium. It was no magnetism, no preheat, no post, no impasse temperature, and once again the 10-to-1 weight savings. So once again, everyone's very happy with the EB welding of the launcher board system. And I was very happy with that because at the end of the day, I just enjoyed that part. And I say, so every day I look at the launcher board system, that is my project up there. So thank you for your attention this morning. And as I say, live long and prosper out there. If you Star Trek fan like I am, live long and prosper. And I thank you for your attention.
Thank you very much. Amazing presentation. I have a question for Captain Kirk.
Okay, thank you very much.
What about residual stresses of the whole detail after the welding?
Did not have the residual stresses like we had early on with the 4340, the titanium. There was no stress relief was required. And that was the good thing about it. No stress relief required.
Does it require some heat treatment or something like this? Or
no, it was not required. That's the good thing about the TI 64 titanium. Once we welded it, and there was no preheat, no post heat required thereafter. It was as welded conditions were excellent for the launch.
mm-hmm.
So that's why I really.
Does anyone else have a questions?
Maybe me. Sorry, it's one room, one room. And my question also about AB welding of titanium details. It's a great idea, I think. And it's easy question about defects. You said about defects after welding and the steels, and the opinion is in the case of when welded after titanium details, it's will be in pure and clear methods. We know about this, and any defects are after welding in weld or seam.
No, I mean the key was when we cleaned the parts, we scraped the parts, manually scraped the parts, and we welded the parts after doing the alkaline clean within 4 hours. Once the parts were clean, we had 4 hours to get it inside the chamber and get it welded, and there was really no defects. We were like 98% pure. We had a little porosity, but all except over to a Class A weld for aerospace D17.1. Our vendor did a great job with the cleaning, guys. I was very impressed, and my EV technician did a great job. We made sure we had a Saki moving gun, and we were very successful with the cleaning process. So there was no defects and no arcing or anything. So made me very happy, made me a hero for the corporation.
Thank you.
You have issues. So every time I use this backdrop, so every time I see my backdrop here, this is my launcher board system. So as I retire from Lockheed Martin, I have a legacy that I left behind me.
Thank you. Great. Very nice. Thank you for your amazing presentation.
Thank you.
Thank you. Does anyone else have any questions? I guess not. So thank you very much for the amazing presentation. You can
My
go
pleasure.
rest now. Yes, it's how many? 3 a.m., 4 a.m. And okay. Thank you. Thank you. So moving on. Next presentation will be from Mikhailo Voron. It's called Production of Fine Crystalline Aluminum-Based Master Alloys by using electron beam casting technology. Please, Mikhailo. Он мне не пытается говорить. Is everything okay, Mikhailo? Okay, yeah. I guess so, but you have your mic switched off. We can't hear you.
I asked, do you see my screen or not?
We see you.
Oh, okay. Good day, everyone. I'm glad to be here with you, and I want to introduce you a small topic: obtaining thin-walled titanium castings in ceramic molds under conditions of electron beam technology.
If you can, can you put it in excuse me, can you put in presentation mode so we can see the full screen?
Oh,
yeah, sure.
I thought that I did it. Something.
I think you need to share the presentation mode, not the presentation itself, but the window with the presentation mode.
I thought I did it. Do you see it now?
The presentation, not the presentation mode.
So help me, please.
Click down here in the lower right-hand corner, the full window, lower right-hand corner.
Near the 70% text on the right lower, on the right bottom corner.
Maybe.
Миш, внизу справа там 70%. Там слева кнопочка, да. Вот это слева, не, слева от 70%. Не-не-не.
Ну, да, я вот нажал, ну видно?
Ну, все равно презентация. Попробуй, когда ты шеришь экран, выбрать именно, там будет отдельная презентация, а отдельно будет вот этот мод презентационный.
Ну, вот я вот окно именно презентации открыл.
Ну, не самой презентация, а там будет отдельное окно еще, типа презентация.
А ну давай вот, ой, не то, сейчас, секунду. Сейчас. Так, видно? А вот так?
Еще пока нет.
Да елки-шпалки. I'm sorry, we'll fix it up. One more time. Так, я выбрал окно презентации. Я им делюсь. И я вот это делаю снова. Видно?
Смотри, ты сделал, а теперь выйди из шеринга и зайди обратно и выбери именно вот эту вот презентацию. Не закрывай. Альт-табом попробуй переключиться.
Да, сейчас попробую. Еще раз. Во.
Да.
Хорошо? О, супер. Thank you. All my excuses for this. Thanks. Our team was inspired by most difficult and responsible titanium parts for medical application. We tried to obtain something like this, not by using additive manufacturing, but using casting technology. So now some kind of such kind of details are usually obtained by 3D additive manufacturing, but we believe and even sure that in some cases thin-walled titanium castings may be much better and reliable for than sintered powders. Maybe it consists of mechanical properties because dense metal we think is better than something with spores and sintered powders. So so we decided to try and choose the electron beam casting technology, one of the main and unique special methods developed in our institute. This technology has many advantages. It may refine metal from harmful impurities, it has independent heating source, and it provides full control of melting process and its duration. So we may do anything we want with this metal during hours, many hours. We may do something like electromagnetic steering, overheating the metal, and many other cool things. And in general, we also may produce ingots and castings and semi-finished products with weight about 15 kilos. As you can see on this slide, our structure of our casted parts is better than in some familiar technologies. The second step was to choose the ceramic materials for producing shells, the molds for investment castings. It was the only reliable method to obtain something very difficult and thin-walled. Due to technological requirements, Gibbs energy, and price of materials, 3 types of ceramics were chosen. Very important thing is that our method provides an ability of using cold mold, while other methods require using of hot molds, heated to about 600 and more degrees Celsius. Different contact shells were produced to investigate the features of ceramic melt interaction. Inner layers were made of chosen 3 types of ceramic, and the outer layer was made of large fraction aluminum oxide. This is an example of our first training molds for puring titanium and obtaining some pieces of metal to investigate mechanical properties and structure. This is our installation, and here we can see the furnace and 2 stages of experiments, before and after. So this is the microstructure of our specimens. We discovered it, and all of them had diffusive alpha layer. We used pure titanium. It's all consists of alpha phase, but we mentioned the contact alpha layer, which is very interesting for us to discover the interaction features with our mold. And specimen A1 shows clear large alpha layer, but it's also has inhomogeneous areas. Z1 and Z2 shows thinner alpha layer and more homogeneous formation of it. And ZS1 and ZS2 spacement has the thinnest alpha layer, but presence of silicon provides hard surface, high surface hardness, and also we discovered some areas with titanium silicon eutectics. Here's the same specimens, but in larger увеличение, забыл слово, the larger view. Yes, thank you. The next step was to produce a real implant. First step was to create a model. We chose the PLA plastic because of its mechanical properties and ability to be printed with as a small detail. Then PLA part was added to polystyrene gutter system and formed into ceramic mixture. After drying and sintering at 1100 degrees Celsius, mold was ready to be cured with titanium. And here's the view of our mold. And here's the example of a detail. As you can see, it's almost perfect as for casting. We can see even the prints of PLA fiber that left from our model. We also compared mechanical properties of our metal with similar examples obtained under other conditions. Here you may see them, and electron beam casting technology, as we can see, allows to produce castings with relatively high properties. Sometimes they are even close to deformed metal. As for us, properties of our casting are more than sufficient for producing prostheses and some kinds of implants. So here are the conclusions. Now we're working on the upgrading our theory and practice of this. Yesterday we tried to get 2 implants like this, and we are trying to get them by using other alloys, like low modulus alloys with high content of zirconium and niobium. And if you're interested, we invite you to make this work. If you're interested, we invite you to join us in this work. Thank you. Do you have any questions?
Thank you for a great presentation, Mikhailo. Yeah, does anyone have any questions?
Yes.
Yes.
I have a question. Okay. Thank you for your presentation. I have a question. In what form you have alloying components you using? It's clean alloying components and or melting?
No. We mostly use secondary materials, deformed plates, but we also used sponge, titanium sponge, and we may use any type of material, from sponge to secondary materials.
Okay. And zirconia, molybdenum.
Also as secondary materials. For our experiments, it's more than sufficient. When we will get some task to obtain something very clear with high mechanical properties, we will take something more clear.
Okay.
And clean.
Thank you. Anyone else? Well, perhaps I have a question then. I know it's a bit unique question. What about gases in your materials?
We haven't tested them yet because it's no chance for us for today to get the analysis, and you know why. It's very expensive. Say hello to Mr. Kaliniuk.
We will say hello to him. Okay, so anyone else? I guess not. Thank you for a great presentation and great post-presentation discussion. And we up for the next presentation. It's Pavlo Kalyuzhny from the Physico-Technological Institute of Metals and Alloys, just like Mikhailo. Is Pavlo...
Yes, I'm sorry, my presentation was instead of Mr. Kalyuzhny. He couldn't be here, so I showed it instead of him.
Understood. So the next one then will be Vitaly Porokhonko, our own native from Patton Electric Welding Institute, with the presentation called Electroslag Remelting with Portion Ingot Formation. So please, Vitaly, all yours.
Hello, dear colleagues and participants of the conference. My name is Vitaly. I am researcher of Patton Electric Welding Institute. I bring to your attention a report on electroslag remelting YSR with portion ingot formation. Electroslag remelting is widely used for the production of ingots from a wide range of steel and alloys. But YSR ingots have disadvantages. They are shown on this slide. It's coarse columnar structure of YSR ingots and liquation defects and segregation. That is why it's necessary to develop methods of influence to the crystallization of the YSR process to increase the structure and chemical homogeneity of the metal and suppress the liquation processes. On the possible ways to solve such disadvantages is to conduct the YSR process a pulsed mode with periodic layer by layer formation of an ingot. The slide shows a diagram of the main parameters of ESR with periodic layer by layer formation of an ingot. The aim of this work was to study the future of the ESR process with a layer by layer formation on an ingot and to study the patterns of structure formation of the smelted metal. This slide shows typical parameters of experimental ESR melting and schematic diagram of experiment installation for ESR with portion heat input. Parameters of the ESR process are necessary to ensure the periodicity of electrode melting and layer by layer formation of an ingot with the height of individual layer varying in experiment from 0.2 to 0.5 of the radius of the ingot. Let's move to results. This slide shows appearance, macrostructure, and crystallization scan of ingots diameter 84 millimeters of alloy cobar. Is this seen that the nature of crystallization depends of the parameters of the pulses and pauses of the remelting voltage. The dispersion of the structure ingot, this is ingot, is much higher than the structure of this is ingot. We also accept covers ingot diameter 120 millimeters of alloy cover. The size of dendrites is larger than the ingot to diameter 84 millimeters, but the macrostructure show a layer by layer crystallization. In addition, experiments we performed on ingots diameter 220 millimeters of this steel. The use of ESRL affects crystallization, but the effects we found on the macrostructure of ingots. The presence of defects is probably related to the pulse during voltage near 600 seconds. Reducing pulse direction time of pause near 216 to 316 provides a quality macrostructure. ESRL ingots are characterized by the absence of large columnar radial oriented crystals and a zone of their cone crystallizations along the ingot axis. a small volume of a metal bus and a good quality of the lateral surface. From ingots 926 samples we were prepared for mechanical test. The scan of cutting symbols shows this picture. Mechanical properties along and across crystallization layer are equivalent. And conclusion, I will not dwell on all, I will only say the most important thing. The possibility of controlling the formation of metal structure during SRL by conduction, the process in impulsed mode, providing layer by layer formation of the ingot was experimentally shown. At the correctly selected conditions of layer by layer formation, defects in fusion zones are absent, and the mechanical properties along and across the crystallization layers are equivalent. Thank you for your attention. Can you ask me?
Thank you, Vitaly. Does anyone have any questions? Okay, then question from me, why mechanical properties are the same in even in both directions? They should be different, I think, from my experience.
Yes. Yes.
У тебя нет микрофона. Включи микрофон.
Agreement. Yes, mechanical properties is equivalent along and across crystallization. It's magnetic metal and depends from this macrostructure.
Okay. Thank you. Does anyone else have any questions? Okay, then. Thank you, Vitaly. Amazing presentation. I want to make a small announcement for our international colleagues and guests. We know it could be very late at night where you are. And if anyone wants to do a presentation ahead of their scheduled time, let us know. We will figure something. We will figure something out. We will just let us know. Okay, we are continuing our section. And the next one is Alexander Khozhanov from East Kazakhstan State Technical University. His topic is research of organometric composition and speed of motion of dispersed particles of zirconium wire during welding. Is Alexander here? Right, of course. So I guess there's no Alexander right now. Alexander should have been the last from this section. Okay, so in that case, the innovative technologies and process of methodology section is over for now. We will have a break and we will continue. We will, how many? We will have a 10 minutes break before we will start the next section at 12:30. EET time, Kiev time, as you want to call it. So thank you, everyone. Have a break. We will be back in 10 minutes.
Hello, everyone. Welcome back. Now we have the section fracture and fatigue behavior of welded components and structures. Unfortunately, one of our presentation is missing today. So now is present the constant and variable amplitude loading of 7,000 series aluminum alloy joints produced by flash butt welding technology. High-strength thermally hardened aluminum alloys have found wide application in industry in the production of various elements and structures of aerospace industry, aircrafts, yachts. These alloys are strengthened by heat treatment while acquiring high mechanical properties and sufficient technological plasticity. At present, for example, for the manufacturing of load-carrying elements, shells, longerons, and etc. of aerospace and spacecrafts are used 7,000 series aluminum alloys, which are mainly use aluminum, zinc, magnesium, and copper alloying systems. They belong to the group of hard to weld or non-weldable aluminum alloys. At the same time, at the present, used such technological process as riveting, but riveting is mainly very laborious, economically demanding, and operation associated with difficult working conditions. And we need carefully, we need to make very careful surface treatment of the rivet hole for a reliable connection of the product, and during long-term operations, the riveted joints is susceptible to loosening, which affects of the service life of the products. In this study, we take a look on the aluminum alloy 7056, which has very high the main feature of this alloy is high zinc content, near 10%, which makes it very hard to weld alloy. We try to make traditional we obtained Promeus we try to weld it in two passes. We using MIG pulse welding. In the inert gas, with 50% of argon and 50% of helium. It was welded in our institute. Microstructure was partly good, but it was very high softening in the middle of the area. More better microstructure, as you can see, this was before as welded joints, and this is after heat treatments. One of the perspective ways to obtain sound joints with less heat treatment is welding in the cold state, such as flash butt welding technology. Using flash butt welding technology gives us good microstructure, but we have some issues according to the heat treatment of this alloy. It was 3351 treatment, which was also not only annealing but also the deformating state. So before welding, it was heat treated, and after that we obtained sound welded joints. Here we can see a macrostructure of as welded and heat treated joints. Heat treated joints also has some issues in the middle of the joints. We have less points in the hardness, but after the heat treatment, it get much better, and we obtain more suitable for fatigue behavior microstructure. Mechanical properties, investigation of mechanical properties was provided on a universal servo-hydraulic testing machine with load range 2500 kilonewtons. We tested specimens that you can see on this picture, and after testing, we can see that welds of 12 millimeter thickness gives with welded with MIG technology gives near 0.5 of base metal, and the flash butt welding give us near 90% of base metal strength. But the main issue of these parts that are welded by this with this alloy is fatigue behavior of this alloy. As we know, many structures work not only in at the constant amplitude loading, but mainly at variable amplitude loading. Structures more less durability and so shorter life. So we use for the variable amplitude loading standard Gaussian distribution and provide fatigue testing on this point. You can see here the program amplitude loading that was used to shorter the fatigue experiment time. So here you can see the main data of provided testing. Here you can see the obtained SN curves on the constant amplitude loading at stress ratio 0.1. The endurance limit on 2 million cycles is 200 MPa, and flash butt welds give us near 130. That give us near 60% of base metal. Specimens tested at variable amplitude loading gives us near the same results, near 200 MPa and 150 MPa at base 2 million cycles. After this, we provide fracture study and provide the investigation of the fracture cross section. We can see that the stage of fatigue crack growth to the state of fracture is more than for crack initial of high strength aluminum alloy with high zinc content can be obtained using flash butt welds. Tensile strength of welded joints show tensile strength near 90% of parent metal, and fatigue behavior under stress ratio 0.1, and variable amplitude loading shows endurance limit near 60% at the endurance limits 2 million cycles. This confirms perspective of using flash butt weld for obtaining joints of high strength aluminum alloys with high zinc content. Thank you for your attention. Anyone have any questions, please?
So I have a question. For me, for welder, it's interesting one fact. You using high strength aluminum alloys. It's MIG methods, and AMG6. It's right?
Welding using MIG technology, one of the best ways to obtain sound. For using flash butt welds, it's not necessary to use any filler material.
Okay, thanks. I understand. My question next.
On one slide, you show us the properties of beam. The seam is in 2 times less than base metal. I think it's a reason why you used more plasticity editing material than base metal. Plasticity like elongation of this welding joint.
Elongation, it was not shown on the slide. The elongation of base metal was near 12%, and used flash butt welding, it gives us near 5-6%. So it's in near 2 times less than parent metal. So yes, these parts of technology need to be improved, or think to use it in the special places where we have a less influence of loading on these elements.
Okay.
Thank you.
Yeah. I would agree with that. I was thinking, did you experience any, what was the elongation in the 7000 series? And did you experience any cracking? Were there any cracking observed in your testing?
Thank you for the question. It's very nice you work with 7000 series. Yes, I haven't shown the fracture of specimens in full photo, but we have cracking along the specimen. It's have a very specific type of fracture, and not only when it crack mainly initiates in the welded joint, but when fracture occurs, it gives the longitudinal cracks in different directions based on the, I think it's mainly the feature of the heat treatment 351, which are mainly have the not only heat treatment, but also how to say deformation along the plates.
Okay. Yeah, I was just curious if you can get away with cracking. You've done a great job, but you still had the cracking issue. So thank you.
Thank you.
Yeah.
Any questions? Okay, thank you for this section. It's last of our presentation. So now we have lunch, and we will continue our conference at 2 p.m. So welcome you in 1 hour to join us.
hard. It's very developed. So at this point,
Hello, everyone. We are welcoming you on our conference. Now we have next session named Advanced Welding and Joining Technologies. So the first presentation will be Bogdan Cherednyuk. Is he here? So просто maybe here is some guests that need to make presentations earlier. We also can add them to provide some presentation if you missed your time. So the next is Vadim Strashko. Okay, then Andriy Timoshenko. So unfair guests, they just don't write to us something about their participants in the conference. Next is Vitaly Polishchuk. So Vitaly Polishchuk is also missed. Hitesha Narsia. Also no. Amadeus Aurin. He has write to us that he will not available to participate. Mykola Kachowski also is not here. So Taras Maidanchuk, will you show us some presentation regarding TIG welding of copper tires with collector plates, motor armature? So please.
Could you please tap your microphone?
Sorry, we cannot hear you. Roman, please switch on microphone.
The connector, sorry.
Sorry, we have some troubles in the about audio connections. I have heard the voice, but everyone else haven't. So we start the presentation from the beginning. Sorry for this misunderstanding.
Видно? One minute. Hello, my name is Taras Maidanchuk. I want to present my presentation. TIG welding of Cooper tires with collector plates, motor armature. Electric motors is various purpose and capacities of widely used in industry. One of the main components in this equipment is the armature of the electric motor, which has different size and diameters. The slide shows some types of anchors. An important technical problem is to connect it of the armature winding with the collector plates, which are made of copper 0. As for today, the connection of armature winding with collector plates in the manufacture of electric motors using soldering, butt welding, and argon arc welding. This uses automatic settings which are designed for large volumes of downloads. However, due to the wide range of type of electric motors and the nature of the connection in the windings to the collector plates, their use is not always appropriate. In the given work to complex of works of development of technology of TIG welding in the environment of argon of steel of argon of copper tires with collector plates of a connector as a started generation DKS 18.8 is executed. The condition of the assembly of the start generator are defined, which allow to obtain a high quality welder. The connection in the automatic made, namely, the gap in the welded joint must be less than 0.3 millimeters. The displacement of the tires relative to each other in the vertical plane is not more than 5%. Tight placement of tires in the grooves of the collector plate. The absence of different thickness of the walls of the groove of the collector plate. Welding in the prototype static generator was performed in the installation layout, which is shown in the picture. The armature was fixed in a rotator on ruler supports in a horizontal position. The banner was mounted locally above the welding area in a device that allowed it to move along the connector lamella in the range of ±5 millimeters. The picture shows the appearance of the full-scale sample after welding. The connector section before welding and after welding are shown in the picture. The main condition for high-quality welding of base bars with connector plates in the absence of lamellar jumpers possible when melting metal. In this case, due to the optimal modes, they are absent. Similarly, due to the high thermal conductivity of copper, the short duration of the welding process and low welding current, there was no burnout of the lamellar plates. As a result of the experimental work, at the cyclogram of the welding process was constructed, which includes a gas page time, current rise time, welding time, current drop time, and gas pour time after the completion of the welding process in automatic mode. It is established then in order to obtain a high quality joints, the welding process is carried out without moving the welding torch, which oscillation with a frequency of 1/120 -1 and an oscillation step of 2 to 4 millimeters. The total welding time of one collector did not exceed 50 minutes. Conclusion: in this work, a set of works in TIG welding in the improvement environment of agon of copper tires with connector plates of the collector of the starter generator DKS 1880 is performed. The condition for the assembly of the starter generator DKS 1880 which allow to obtain high quality welded joints in automatic mode. As a result of the conducted experimental works, the cyclogram of process of welding is constructed. Technology parameters of welding are defined. The development technology is quite rational in the manufacture as a small number of starter generators, such as DKS 18.8, as it does not require specialized expensive installation. Thank you for attention.
Thank you for your interesting presentation, Taras. Have everyone some questions? So there is no questions. Maybe I will ask some. As I know, in the nuclear power stations, they use soldering in such types of connections between the main part and the chips. So why welding is better?
The soldering process is widely used in industry, but in this components have low electrical conductivity because the joining with weld is better because the electroactivity is only 100% of poor copper.
Okay, thank you for your question. Thank you. Anyone questions? No. Thank you, Taras, for interesting presentation. Have a nice day. So the next session. Sorry for this. So the next presentation is from Roman Kolesnik, improvement of heat elements efficiency for resistant welding of thermoplastics. Please, Roman, take the place.
Hello, everyone. Can you hear me? Hello. Can you hear me?
Roman, we can hear you, please.
So sorry,
no, there is.
No.
Please, one more time.
Hello, hello.
Okay, it's okay. You can take the place.
Okay. So hello, everyone, dear colleagues. Let me introduce you a presentation concerning improvement of heating elements efficiency for electrofusion for resistance welding of thermoplastics. So the technology of resistant welding is next. Between the adherents to be joined, placed a heating element commonly made of stainless steel mesh, and when a current flows through it, it heats according to the Joule-Lenz's law, and under the pressure forms a welding joint. The most prominent benefit of this type of welding is can you hear me? So hello.
It's okay, we can hear you.
Okay, but because I don't have a feedback, so we can join geometry of complex geometry joints. But the problem of this technology is poor adhesion between a heating element made of metal mesh and the polymer. So this problem can be solved by using heating elements with better adhesion to the polymers, and use heating elements which can be formed from the electroconductive polymer composite. So the aim of the work is to optimize the property of metal and develop composite heating elements, and to study the influence of mechanical strengths of welding joint. In this work, we used two types of polymers, high-density polyethylene as a model to evaluate the efficiency of this technology, and high-tech polymer polyaramid, which widely used in aircraft industry. Metal mesh heating element was used from stainless steel mesh and titanium mesh. The surface of this element was modified by chromium, steel, 1066, molybdenum, and titanium. Heating element made from electroconductive composite was made from high density polyethylene and was filled with carbon black and carbon fiber. So, as you can see from the pictures, the surface of unmodified heating element is smooth. In this case, the specific area of contact between polymer and the heating element is low. So, modify it. Otherwise, modified heating elements, as you can see from this the picture, have high specific.
Sorry, Roman. Can you start your presentation because we see the all slides? Maybe you can check the
all?
F5. Yes. Maybe you start your presentation because we see see now we see 5 slide. Yes, slide number 5. Yes, it's okay because all this time we show just first slide.
First one, yeah.
Yeah.
So maybe I share the screen one more time. Do you see the switch of the slide? Okay. The specific area in this case is higher, and mechanical contact between polymer and the heating element is better. You need to know that with increasing the depth of the coating, the specific area additionally increase. By using this modified heating element to weld the butt joint with chromium and titanium contact, you can see from the diagram that increase in strength is to 10%. So on a model high density polyethylene. So further works was conducted on high-tech polyethylene, and in this case we can see that the best results was got in by chromium coating, which provided increase in strength to 13% on soft welding mode, which characterized by high welding time and low power of welding process. In case of chromium coating, a fracture was conducted by the heating elements, which tells us that it increases the strength of the welding joint very high. Also, we conducted the experiments by using titanium metal mesh with a modified surface. In this case, we also observed increasing strength by 50%. Decreasing strength can be it can be shown that there were defects in the welds, such as pores and different other defects. So we get a result by increasing welding strength to 13%, but it's not satisfied our demand. So we switch our heating elements to heating elements based on electroconductive polymer composites. made of high density polyethylene and filled with carbon black, which is electroconductive. In this case, as you can show on the slide, during electrothermal measurements, the best results we got was on composites filled with carbon black, since composite filled with carbon fiber and combined filler carbon fiber carbon black has decreased in temperature when we applied a certain voltage. This can be.
Ramon, sorry, I'm sorry for interrupting. We still can only see the fifth slide. Can you?
Fifth. Okay.
You turn the
and now
on?
Now
we see the 11th slide, but we don't see the changes of the slides. So your comments are kind of missing.
Okay.
Maybe you can return a few slides back and proceed from there.
Which
and
slide
turn on. Yeah, maybe from here and turn the presentation mode on, please. F5, I suppose.
KF5.
KF5.
Fine.
Because you're staying on one.
So we still only see the 8 slides in like general view of the PowerPoint.
If I turn a slide show, you don't see the changing of the slide.
Yeah.
So maybe I just turn them right here.
Yeah. Maybe you can show it like this. Okay. Yeah, it will work. Thanks.
So which slide I should start with?
Maybe you can return to slide number 6 or 7, and we can go from there.
6. Okay, 6.
Yeah. Okay. Sorry for that. Yeah.
No. So to be back, so you saw information about modified metal mesh, and we use this metal mesh to have a butt weld of polyethylene, and as you can see from the diagram, it was an increase in strength by 10%. So further, we use these heating elements to weld high-tech polyethylamide, which widely used in aircraft industry, and the best results was obtained by using nichromium coating, and increase in strength was at a level of 10 and 13% on the soft welding mode, which characterized by high welding time and low welding power. As you can see from the fracture surface of the welds, in the case of nichromium coating, fracture was conducted by the heating element. Decrease in strength caused by such defects as holes and other one. Also, we used a metal mesh made of titanium. As you can see from the diagram, it also observed an increase in strength to 15% in comparison with standard metal mesh, unmodified metal mesh. But increase in strength to 13% is not satisfied our demands. So we transfer to the heating elements based on electroconductive polymer composites made of polyethylene and was filled with electroconductive carbon black and carbon fiber. But in case of using composites filled with carbon fiber and combined filler carbon fiber and carbon black, we can see a decrease in temperature after applied a certain critical voltage connected with positive temperature coefficient caused by thermal expansion of a polymer matrix. So further, we used composites filled with carbon black by increase filler content to 12 and 16 volume percent. And in this case, composites generates heat, but it ununiform distributes along the surface of the heating element and welds join only in the area where the temperature was higher than the melting temperature of the polyethylene, which is 130%. So further, we increased the filler content to the 30 volume percent, and in this case, after applied of value of 5 volts, the composites heats to the temperature of 200 degrees Celsius, which is much more than the melting temperature of the polyethylene. In this case, also the thermal conductivity of the composites increase, which has a positive effect on our heating elements. After that, we use these elements to weld lap joint and butt joint, and effectively use them. As you can see from the pictures, the temperature that generated by this heating element is sufficient to form a weld. The welding modes were the same as for modified heating elements. Hard mode, which characterized by high voltage and low welding time, and soft mode, long welding time and a stepwise increase in voltage. The best results was obtained by using the soft mode. Depending on the welding mode, also resulted in the fracture of the welding joint. In case of hard welding mode, it, as you can see, the melting of the surface in the heat affected zones is poor, and the fracture is brittle. In case of soft mode, as you can see, polyethylene melts better, and fracture is more than plastic. Overlap joints fracture by basic material, which tell us effective using this heating element for joining plastic. So according to these results, we built a diagram which has 4 zones. In first and 2, there is we can form a welding joint, and in 3 and 4 there is no obtaining a welding joint because of lack of power or it excessive. So we can conclude that by modifying metal heating elements, we can obtain an increase in strength, and we found regimes that can form a welding joint with increasing strength. It was found that in composite filled with carbon fiber and mixture of carbon black and carbon fiber, there is a positive temperature coefficient with consisting increasing the electrical resistance of the conductive phase for the filler due to the thermal expansion of the composite, and further we used composite filled with the carbon black. Also, it was established that the modes with increased welding time and stepwise increase of specific power of the welding process ensures the formation of a strong weld wells. According to these results, we built a diagram which is a criteria for formation of welding joint. So thank you for your attention.
Roman, thank you for your presentation. Anyone has questions to Roman, please?
Okay, I have a little question. Thank you for your amazing presentation. It's topic very actually in this time and nowadays. I have a little question, just interesting for me because I'm specialist in welding of metals and other plastics. But interesting for me, it's can you show the slide like 14? 12.
12.
Yes. I see joint process, yes, and you subscribe this process. Is this high temperature about 120 degree? And how the method you subscribe these pictures? It's like just only photo from your phone, or maybe some like filters or like etc.
The temperature was measured by a special thermal imager, which after which in the program we measure the temperature of the surface of the composite.
Okay, I understand. Thank you. Design for your pictures. Thank you.
Thank you for your answer. It was very interesting presentation. So next will be the section due to absent participants. It's new structural and functional materials, nanomaterials, and composites. So the next presenter is Alexander Kremenchutsky. Please take the floor and show us what you got. Alexander, are you with us, or you need? Oh, Alexander asked to the chat that can't participate. Okay, Alexander, then the next is Galina Mikhailova. Please make the presentation. Okay, Galina, please turn on your microphone and.
Yes. Okay. Are you hear me?
Yes, it's good. Thank you.
So I want to present you the report with the same changing of the properties of carbon nanotubes under external influence. What is why nanotubes is being the so nice? They have initial properties. They combine high strength and elasticity, thermal and electrical conductivity, and mechanical deformation and influence the electric structure, concentration of the charge carriers, electrical emission, and other properties of TNT. Defects arise both in the process of synthesis, growth, such as or with the external influence, especially in radiation. That's why these structures are interesting to research. So we need to study radiation defects due to the possibility of using nanotubes in space and nuclear reactions, as well as to use a high energy radiation as a technological tool to create radiation defects and obtain material with fundamentally new properties. So we study various types of carbon nanotubes after electron and gamma radiation. These are examples of photos with different cathodes. Carbon nanotubes in a bulk state are electrical not conductive, and for transition to the electrical conductivity state, it is necessary to establish an electrical contact both between neighbors nanotubes and with electrodes. Therefore, CNT were placed in the electric cylinder under a piston. With a decrease in value, the circuit between the electrodes closed and the system passed into the electrical conducting state, which corresponds to the dielectric metal transition and is accompanied by a sharp increase in electric conductivity as a result of reorientation of CNT and their compression. Then it reaches a maximum and with subsequent component is smoothly described. In the situation with a single wall carbon nanotubes, electrical conductivity is 50 times lower than multi-walls ones. This difference is due to the different types of conductivity in CNTs. At low densities, the volt-ampere characteristics of the multi-wall carbon nanotubes has a non-linear symmetric form, which indicated van der Waals encrustion and two-node transitions. And at the high densities, it is a linear dependence, so metal conductivity, and the single wall nanotubes have a asymmetric volt-ampere characteristic for all compression densities, which indicates the semiconductive nature of the conductivity. It's shown in this represented colors. Penetrating radiation causes not only radiation damaging materials, but also serves as effective technological tool for improving the quality and obtaining materials with fundamentally new properties. Multi-layer carbon nanotubes with 18 nanometers in diameter were irradiated with gamma quantum with a dose up to the 3.3 to 10 to the 17th gamma quantum per centimeter squared. After exposed to radiation, the characteristic of electric conductivity curve changes. It grows is less gradual due to the change in the structures of CNT and the appears defects at the stage of unloading, and notable change in the shape of the electrical conductivity curves is obtained in comparison with the situation before irradiation. For unradiated CNT, the elastic limit is 18%. After gamma quantum radiation, a minimum is observed on the dependence on the elastic limit of the radiation dose. This indicates the formation of defects at low dose of gamma radiation. Defects practically do not lead to the decrease in the elastic limit after annihilating it slightly increases, but their interaction with radiation causes a decrease in elasticity and critical density by almost 4 times as a result of increase in the color of their shape due to the formation of topological defects. Growth and radiation defects in CNT change their shape and form a topological disorder. Their joint action more or less distortion of the CNT shape, which implicates the interaction of defects of different genesis and their heating as a result of the combination of knocked out carbon atoms. The impact of the CNT array with both electrons and gamma, contributions to significant increase in electrical conductivity, which is due to the complex nature of the interaction of primary and radiation defects. Primary defects compensate for the effects of radiation defects on electrical conductivity. Each of the topological defects of graphene wires of different genesis separately destroy the shape of the nanotubes from the rectilinear one and form a topological disorder as the decreased electric conductivity and increase it the by coefficient alpha. The dependence on the specific magnetic moment of the magnitude of the magnetic field strength in the reference CNT sample has the form of a hard magnetic ferromagnetic. Catalysis in initial state has a hysteresis with characteristic of a superferromagnetic. Compression of the cover shows that after the transition of the catalysis from a massive initial state to an uncrystalline one inside the CNT, its magnetic state changes from superferromagnetic to ferromagnetic and accompanied by an increase by the factor of 2.5. The effect is associated with the height in the top of nanoparticles with a diameter more than 10 nanometers formed inside of TNT, which stabilizes the magnetic ordering at room temperature. Gamma irradiation with a dose up to 10 to the 7 gamma quantum per centimeter squared, with to increase in the coefficient alpha by a factor of twice and starting thousand graphene wires. And defects of various genesis, growth, and irradiation deviate the shape of the TNT from rectilinear and form a topology of the solid. Thank you for your attention. Maybe you have some questions.
Thank you for your interesting presentation. It was very interesting and specific for our institution. So anyone has some questions, please? So everyone likes your presentations and no one has questions because it was clear for them. So thank you, Halina, for your presentation. The next one will be our guest from Kazakhstan, Alexander Kazhanov from the Srikhalviev East Kazakhstan State Technical University. Please, Alexander, take the ground and make your presentation, please.
Hi guys, can you see my screen now?
Yes, it's okay. Yes, we
Yeah.
hear you. You can start the presentation.
Yeah, so today I'm presenting the research of granulometric composition and speed of motion of dispersed particles of zirconium wire during microplasma spraying. Modification of implant surface can improve not only mechanical properties of the implant, but also enhance its biological activity and osteoconductivity at the cellular level, as well as increase antibacterial properties of the implant surface. Currently, thermal spraying methods are widely used in applications related to the metalworking industry, but for the biomedical field, it is innovative issue with a potential that is currently being studied. One of the factors that prevent the introduction of thermal plasma spraying technologies in the production of biocompatible coatings is a possible heating of the implant during the process of coating decomposition with a jet of high temperature plasma, which can lead to changes in its shape and mechanical properties. The use of microplasma spraying technology allows avoiding volumetric heating of the implant due to the low power of the process, up to 2 kilowatts. The formation of thermal plasma coating is characterized by the ingress of large numbers of particles more or less melted in the plasma jet, forming so-called splats, between which pores are formed. Herewith, the porosity and roughness of the coating surface depend on the size, speed, and degree of heating of the particles forming it. The pore size is affected by both the actual size of the coating particles and their shape. Understanding the mechanisms of coating formation allows selecting specific parameters of thermal plasma spraying to obtain the desired microstructure of the coating. The use of robotic microplasma spraying allows for precision coating decomposition on complex shaped implants parts, such as parts of elbow and hip replacements. In our previous papers, it was shown that robotic microplasma spraying can produce coatings on medical implants made of biocompatible titanium and hydroxyapatite materials with a desired porosity and roughness. meeting the requirements of international standards for implants for surgery in terms of coating adhesive strength, crystallinity, and purity. Research, due to its high strength and chemical stability, zirconium is promising as an orthopedic biomaterial. Zirconium has a high resistance to biological media, even higher than titanium, and excellent biocompatibility, due to which it is used for the creation of bone, joint, and dental prostheses, as well as surgical instruments. In dentistry, ceramics based on zirconium dioxide are material for the manufacture of dentures. In addition, due to its bioinertness, this material serves as an alternative to titanium in the manufacture of dental implants. The coatings were deposited by microplasma spraying of 0.3 millimeters diameter wire from grade 702 unalloyed zirconium, and you can see the rest of the material and methods. On the next slide, you can see the technological equipment that were used. Here we can see the parameters of microplasma spraying of zirconium wires. The study of coatings and particles microstructures has been carried out using the instruments shown here, and by processing the obtaining images, the coordinates of at least 20 points of the line forming the profile were determined. Using these coordinates, using MathCAD software, a metallization figure was constructed, and the Gaussian normal distribution function describing it was determined, by which the area of metallization figures was determined. Here you can see the dependence of porosity of the coatings on microplasma spraying parameters in different runs, and the cross-section images. Here are the results of constructing experimental profiles of metallization figures for various spraying runs. Here are the values of material utilization coefficient or factor, and the parameters of metallization figure depending on different microplasma spraying parameters on the zirconium wire. The regression equation makes it possible to assess the influence of each microplasma spraying parameter on the material utilization coefficient. It is possible to correlate the temperature and the speed of particles before the collision with the substrate to the resultant structure of the coating. And the effect of microplasma spraying parameters on the value of the material utilization factor or coefficient and on the porosity of the coating has been established by the methods and of regression analysis. The possibility of the controlling the porosity of microplasma coating made of zirconium wire in the range from 2.8% to 20.3% by changing the microplasma spraying parameters was ascertained. And here are plans for the future experiments. Thanks for your attention.
Thank you for your interesting presentation, Alexander. Anyone has any questions, please?
Hello. I have a question about your process. On your slides, you show the process you make on the air by like robot Kawasaki. If I show in the first slides, is true, yes?
Yeah.
But you used base metal is titanium. It's true, of course. Yes.
Yes.
Okay. How about quality? Because titanium is chemical activity material. And any defects on this surface after spraying is clear process because you do it on the open air, not in chamber.
Yeah. So for now, we just estimated the porosity that was obtained by spraying that. I think we will do that in the future analysis and experiments.
Thank you.
Thank you for your presentation. We're glad that our colleagues like Sergey Venerovich has such colleagues in the other countries, and we can share such technologies and work together. So thank you for your interesting presentation and hope for good cooperation in the future.
Yeah,
thank you again.
thanks.
So the next, there is the end of this section, and now we have the next section is numerical simulation and modeling of processes and materials. And next presenter is Bogdan Sarek with the development of a mathematical model for prediction residual stresses and strains at FSV. Please, Bogdan, take your place and make a presentation.
Hello, do you hear me well?
Yes, we hear you clearly, please.
Okay, do you see my screen?
Not exactly, just a moment. Yes, it's good. You can start.
Okay, super. My presentation, ladies and gentlemen, I want to present you presentation about development of mathematical model to determine residual stresses and strains at the friction steel welding. Friction steel welding was invented in 1991 in the Cambridge, in the Welding Institute. Here we have, here show the building of the Welding Institute in Cambridge and the plane Eclipse 500. This plane was This plane was used the friction steel welded technology for connection the skin instead of rivet connection. Friction steel welding have a wide FSV is widely used for the manufacture of high-tech products. Today, here is shown the largest ship, Superliner Osagawa, the largest friction steel welded ship so far. Also, friction steel welding used in aerospace, automotive, railways, bridge, and producing personal computers. 4GT was produced full tank of 4GT was produced with friction steel welding. Also train in UK and pedestrian bridge in Canada also use this technology. Even APA for the 2012 iMac to effectively join the bottom to the back of the device used friction steel welding. During FSW, friction steel welding process, the working tool is immersed in the metal of the welded joint, rotate and moves along the joint. Friction force generate heat, and that's why we have the joint. Here we have the numerical model of for the friction steel welding of butt weld. Here are represent model of temperature problem, heat. Here we have the heat source for FSW and for the arc welding. For friction steel welding, we use heat source is equal coefficient of friction multiplied to normal force in the contact point and circle velocity, and then multiply it on our radius. After fair modeling, we have diagrams of welding diagrams of temperature for aluminum alloy, for TIG welding and FSW welding. Here we can see that temperature by TIG welding is much greater than that for FSW welding, and also area of the weld of the highest temperature is much greater, like for friction steel welding. Here is results of numerical calculation of longitudinal plastic strains distributions. The strains, the highest value of strains for the TIG welding and for FSW welding is fast equal, but area of TIG welding is much greater. But for the transverse plastic deformation, it is another situation. For the FSW friction steel welding, this deformation have lower, three times lower level that for the TIG welding. This situation we have also for residual stress. In longitudinal residual stresses, we have graphics of longitudinal residual stresses, and value, maximum value is fast equal, but also area is not equal, and area of longitudinal stresses for a TIC is much greater. But transverse residual stresses, for transverse residual stresses, we have another situation. For transverse residual stresses for FSV, friction stir welding, it's much, they have lower level, 3 times lower level than for TIG welding. Comparison, also we have good agreement with our experimental data and calculated data. Here is shown tensometer, and here shows experimental data and graphic of experimental data for longitudinal residual stresses and calculated data. Conclusions. We have effectively developed of model of for friction stir welding, and for friction stir welding we can see also the residual stresses and plastic deformation, but they are much lower than for TIG welding. Also, experiment and calculated data have a good agreement, and I want in the future I want to research the dependence of friction coefficient of material temperature, and also additional heat release by plastic deformation of material and degradation of mechanical properties of aluminum alloy during heating, and also material mixing. Thank you for your attention. Please.
Thank you for your interesting presentation, Bogdan. Anyone has any questions, please?
Hello, thank you for your really interesting presentation, for your modeling processes. But I think interesting for community to compare these experimental results, because we show modeling and the difference between ABV process and TIG. You know, in this case, ABV on your models really better, but you compare this modeling with real experiments.
Yes, yes.
It's really interesting to show in this presentation.
I think he wants you to show on the one picture the difference on the experimental and the calculation method. It will be more good for audience to understand the results. The 20% difference on 5% difference, it will be good to show it on one slide as a comparison. Also here on this slide you can see distance from weld line, okay, and you need to indicate that distance can be negative. It need to be in one side 20 millimeters and other side 20 millimeters. It can't be negative. It's just you need to indicate this on all slides. Distance from weld line can be negative. You need to correct this on these slides everywhere. It will be questions on your from everyone.
Okay. It's depending from the coordinate system.
We can't hear you. Sorry. your microphone is
turn on.
Okay. Sorry. It's just me. Sorry.
It's dependent on coordinate system, where located this coordinate system. Our coordinate system located in the middle of the plate. That's why we have 0 point here, and that's why value of this axis is so.
Okay, thank you for answers. It's very interesting topic for audience, I think, mainly the calculation part. Anyone has more questions, please? Okay, thank you, Bogdan.
Thank you all.
Good luck in your finishing the job well. Okay, thank you. I will give the word to our head of young scientists.
Hi everyone again. I'm glad to see you in Helsol, and thank you for you took part in this event. We planned this event about 3 years ago on YPIC 2019, our last WRTYS conference. That was great big event, and we hoped that event will be in offline mode, but situation is not in our country, all over the world, it's not good. And we must to do this conference just in digital mode. I think in the future it's good idea to do the YP conference for young professional in welding field and welding process and related technologies in digital mode and in offline mode. Thank you for all for your attendance and took part in our conference. In near future, I think the deadline next week. All of you take abstracts in online book abstracts and certificate of attendance. Thank you all. If you have any question to all, and also I want to thank you for all our organization team, Young Scientist Council, Scientific Secretary, our director of our institute, for all welding community, for IAW or Nestle Bird, and all of you for attendance. If you have any question, maybe you can ask me. Okay, I'm glad to see you, and I hope we see you in nearest future in good places in many cities in Europe or world in offline mode. Thank you for your attendance and took part in our conference. See you.